CIET NCERT presents audiobook Ganit Manjari Part 1, Textbook of Mathematics for Grade 9.
Chapter number 8, Predicting What Comes Next, Exploring Sequences and Progressions. Page number 174. On the top right corner, you are provided with a QR code, scanning which you can reach out to the additional resources to this chapter. 8.1 Introduction to Sequences. We observe patterns around us everywhere, be it in nature, in art, in music, in finance, and in many other contexts in everyday life. Patterns help us make sense of the world and predict what comes next. In mathematics, sequences are special kinds of patterns formed by numbers or other objects arranged in a particular order. By understanding sequences, we can explore fascinating ideas about how numbers grow, shrink, or repeat, and even use these ideas to solve real-life problems. In this chapter, we shall explore patterns in sequences of numbers. We will then find rules to help us predict more numbers of the sequence. Let us begin by observing some number sequences that you have already learnt in grades 6, 7 and 8. 1, 2, 3, 4, 5, 6 and so on are natural numbers. 1, 3, 5, 7, 9, 11 and so on are odd numbers. 1, 3, 6, 10, 15, 21 and so on are triangular numbers. 1, 4, 9, 16, 25, 36 and so on are square numbers. The three dots indicate that the sequence continues indefinitely. Think and reflect. Can you describe the pattern in each of the above sequences? Can you predict the next few numbers in these sequences? Before we proceed, let us define a sequence as an ordered list of numbers where each number is a term of the sequence. Thus, in the sequence of square numbers, 1 is the first term, 4 is the second term, 25th is the fifth term, and so on. Also, sequences may be finite or infinite. The sequences mentioned here are infinite, but the sequence 6, 12, 24, 48, 96 is a finite sequence of 5 terms. Can you think of other finite sequences that you observe in your daily life? Page number 175. As you already know, in the sequence of natural numbers, every number or term is one more than the previous number. In the sequence consisting of all the odd numbers, there is a difference of 2 between any two consecutive terms. In the sequence of triangular numbers, the difference between consecutive terms among the first 6 terms are 2, 3, 4, 5 and 6. We may rewrite the triangular numbers in the form of sums of natural numbers as 1 is equal to 1, 3 is equal to 1 plus 2, 6 is equal to 1 plus 2 plus 3, 10 is equal to 1 plus 2 plus 3 plus 4 and so on. Thus, each term of the triangular number sequence is the sum of the natural numbers up to that term. For example, 15. The fifth triangular number is equal to 1 plus 2 plus 3 plus 4 plus 5. This is represented by the diagram as given in figure 8.1, where each triangular number is represented by a triangular array of dots. Can you make the pattern for the next two terms of the sequence? Here in figure 8.1, the first 5 triangular numbers have been represented with the help of tokens. For 1, there is 1 token. For 3, we have 3 tokens, 2 at the base and 1 in between them on the top. Likewise, for 6, we have 3 at the bottom, 2 above them and 1 over the 2 tokens, thus forming 6. And in the next one, we have 4 tokens at the base, then we have 3 tokens on the top of that and again 2 tokens on that and 1 at the apex. So they form 10 here, and in the next one we have 5 tokens at the base, then you have 4 tokens on them, above that we have 3 tokens and then 2 and 1 at the apex, thus forming 15 number. Let us now shift our attention to the sequence of square numbers 1, 4, 9, 16, 25, 36 and so on. Note that the differences between consecutive terms for the first 6 terms are 3, 5, 7, 9 and 11. Also, 1 is equal to 1, 4 is equal to 1 plus 3, 9 is equal to 1 plus 3 plus 5, 16 is equal to 1 plus 3 plus 5 plus 7 and so on. Each term in the square number sequence is the sum of the odd numbers up to that term. This interesting relationship between the odd numbers and square numbers can be represented by the diagram in the given figure here 8.2. Can you explain the relationship? You may recall some of these ideas from grade 6, chapter 1. On the right side, we have figure 8.2 in which square numbers and odd numbers have been represented. We have the odd numbers in yellow and alternately in yellow and blue. It starts with yellow, then we have 3 blue tokens. In the next row we have 5 yellow tokens, then we have 7 blue tokens and likewise 9 yellow tokens, then 13 blue tokens, then we have 15 yellow tokens and then 17 blue tokens, thus representing square numbers and odd numbers. Page number 176. Exercise. Consider the sequence 1, 4, 7, 10, 13 and so on. Can you predict the next 4 terms? Can you derive the first 10 terms of the sequence obtained by adding all the terms up to a given term of the sequence? The hint provided is the first term is 1. The second term is 1 plus 4, that is equal to 5. The third term is 1 plus 4 plus 7 is equal to 12 and so on. In some sequences like the ones described till now, the terms follow a certain pattern, a rule or order. To describe these rules, it is helpful to have a convenient notation to describe a sequence. We can use T1 to represent the first term of the sequence, T2 to represent the second term and so on. In this notation, the subscripts match the term numbers. Thus, for the sequence of odd numbers, T1 is equal to 1, T2 is equal to 3, T3 is equal to 5, T4 is equal to 7 and so on. This notation helps to connect the position of the term to the actual term. For example, T4 is equal to 7 tells us that the term in the 4th position is 7. We may need to talk about more than one sequence at a time. We can use different letters for these. Hence, we can use T1, T2, T3 and so on for one sequence. S1, S2, S3 and so on for another one, U1, U2, U3 and so on for a third sequence and so on. Exercise. Can you write T5, T6, T7 and T8 for the sequence of triangular numbers? There can be many kinds of sequences. For example, the terms could be fractions or negative integers. The ones we have discussed so far have terms that are increasing. But there could be sequences such as 1, 1 upon 2, 1 upon 3, 1 upon 4 and so on, where T1 is equal to 1 and the following terms are unit fractions occurring in decreasing order. We can also have sequences such as -7, -3, 1, 5, 9 and so on, where S1 is equal to -7 and consecutive terms have a difference of 4. Note that when we use the notation Tn for describing a term, n is always a non-negative integer. But the term itself can be negative or in fact any real number. Think and reflect. Can you think of any other kinds of sequences? List out 5 different types of sequences and discuss their properties with your friends. 8.2 Explicit rule for a sequence. Using the notation Tn or Sn or Un, we can write an explicit rule for the term in the nth position of a sequence, that is, the nth term. An explicit formula uses the term's position number n to calculate its value. Page number 177. Example 1. Consider the expression un is equal to 2n minus 1. This states that the nth term of the sequence is given by the rule 2n minus 1. When we substitute 1, 2, 3 and so on for n in the expression 2n minus 1, we get u1 is equal to 2 into 1 minus 1, that is equal to 1. u2 is equal to 2 into 2 minus 1, that is equal to 3. u3 is equal to 2 into 3 minus 1, that is equal to 5, etc. Thus, un is equal to 2n minus 1 is the explicit rule for the nth term of the sequence of odd numbers. Think and reflect. Why it is useful to have an explicit formula for the nth term of the sequence. Using an explicit formula, we can find the 20th term, the 53rd term and 300th term or any term of the sequence directly by just substituting the appropriate value of n. If we have an explicit formula, we can find the value of the term without having to know the value of previous terms. Exercise. Using the explicit rule un is equal to 2n minus 1, find the 53rd term, the 108th term and the 1170th term of the odd number sequence. The explicit rule is useful in other ways too. We can use it to check if a certain number is a term of a sequence and also find the position of the term. For example, consider the odd number 137. To find which position it occupies in the odd number sequence, we need to solve the equation un is equal to 137. This means 2n minus 1 is equal to 137 or n is equal to 69. Thus, 137 is the 69th term of the odd number sequence. Example 2. As another example, consider the sequence that is generated by the explicit formula Sn is equal to 5n minus 2. Can you write the first 6 terms of the sequence? What is the 100th term? The 1000th term? Let us check if the numbers 308 and 473 are terms of the sequence. We solve Sn is equal to 308, that is 5n minus 2 is equal to 308. This leads to 5n is equal to 310 or n is equal to 62. Thus 308 is the 62nd term of the sequence. Similarly, solving 5n minus 2 is equal to 471 leads to 5n is equal to 473. n is equal to 94.6. Since 94.6 is not a natural number, we can conclude that 471 is not a term of the sequence. Can you explain why we need n to be a natural number? Think and reflect. Can you find the rule describing the nth term of the sequence of square numbers? Here is the sequence of the first 10 prime numbers: 2, 3, 5, 7, 11, 13, 17, 19, 23, 29. Do you observe any pattern in the sequence? Page number 178. Can you think of a rule that can predict the next few prime numbers? Exercise. Consider the expression Tn is equal to 3n minus 7. First part. Find its first, second, third, 12th, 18th and 50th terms. Second part. Which term of the sequence is 332? Third part. Is 557 a term of the sequence? Why or why not? 8.3. Recursive rule for a sequence. So far, we have used a formula in terms of n for the nth term as the explicit rule for a sequence. There is another way of writing the rule for a sequence. Consider the sequence 1, 4, 7, 10, 13 and so on. The nth term is Tn is equal to 3n minus 2. Verify this for yourself. Note that each term is 3 more than its previous term. Thus, T2 is equal to T1 plus 3, T3 is equal to T2 plus 3, T4 is equal to T3 plus 3 and so on. In general, we can say Tn is equal to Tn minus 1 plus 3 for n greater than or equal to 2, or we can describe the sequence as T1 is equal to 1, Tn is equal to Tn minus 1 plus 3, where n can take the values 2, 3, 4 and so on. This way of describing a sequence by relating terms to previous terms is known as a recursive rule or recursive formula. If you know earlier terms of the sequence, then you can find the next terms using the rule. Note that the earlier terms need to be known to us to use the recursive rule to find the next terms. Example 3. Find the first 4 terms of the sequence given by the recursive rule. u1 is equal to 1, un is equal to 2 un minus 1 plus 3 for n greater than or equal to 2. Is 133 a term of the sequence? We successively insert the values of n as 2, 3, 4, etc. and compute the values of each term. u2 is equal to 2u1 plus 3, that is equal to 2 into 1 plus 3 is equal to 5. u3 is equal to 2u2 plus 3, that is equal to 2 into 5 plus 3, that is equal to 13. u4 is equal to 2u3 plus 3, that is equal to 2 into 13 plus 3 is equal to 29. Thus, The first four terms of the sequence are 1, 5, 13, 29. Calculating subsequent terms, we can check if 133 is a term of the sequence. Example 4. Find the first four terms of the sequence given by the recursive rule. S1 is equal to 3, Sn is equal to Sn minus 1 within brackets Sn minus 1 minus 1 for n greater than or equal to 2. Substitute the values of n as 2, 3, 4, etc. and compute the values of each term as follows. S2 is equal to S1 within brackets S1 minus 1, that is equal to 3 into within brackets 3 minus 1, that gives 3 into 2 is equal to 6. S3 is equal to S2 within brackets S2 minus 1 is equal to 6 into within brackets 6 minus 1, that is equal to 6 into 5, that is equal to 30. S4 is equal to S3 within brackets S3 minus 1, that is equal to 30 into within brackets 30 minus 1, that is equal to 30 into 29, that is equal to 870. Page number 179. Virahanka Fibonacci sequence. A recursive rule or formula does not only have to involve the previous term. It could involve the previous two or more terms. The most famous example of such a sequence is V1, V2, V3 and so on, where V1 is equal to 1, V2 is equal to 2 and Vn is equal to Vn minus 1 plus Vn minus 2. For n greater than or equal to 3, we compute V3 is equal to V2 plus V1, that is equal to 2 plus 1 is equal to 3. V4 is equal to V3 plus V2, that is equal to 3 plus 2 is equal to 5. V5 is equal to V4 plus V3, that is equal to 5 plus 3 is equal to 8. So, we get the sequence 1, 2, 3, 5, 8, 13, 21, 34 and so on, where each term is obtained by adding the previous two. Can you write the next two terms of the sequence? Do you recognize this sequence from previous grades? That's right. It is the Virahanka Fibonacci sequence. It was first written down explicitly and studied by Virahanka in his work Vritjati Samuchya. In the 7th century CE, he discovered it in the context of Prakrit meter and poetry. It was further studied by the linguist mathematicians Gopal c. 1135 CE and Hemchandra c. 1150 CE. The sequence was later also studied by the Italian mathematician Fibonacci c. 1200 CE. The Virahanka sequence plays an important role throughout mathematics and science. We will encounter it again many times in later grades. Exercise set 8.1. Question number 1. Find the first 5 terms of the sequence in which the nth term is given by first point Tn is equal to Tn minus 4. Second part Tn is equal to 2 minus 5n. And third part Tn is equal to n square minus 2n plus 3 for n greater than or equal to 1. Second question. Find the 10th and 15th terms of the sequence Tn is equal to 5n minus 3 for n greater than or equal to 1. Question number 3. Determine whether 97 and 172 are terms of the sequence Tn is equal to 5n minus 3 for n greater than or equal to 1. Question number 4. Which term of the sequence Tn is equal to 5n minus 3 for n greater than or equal to 1 is 607? Question number 5. A sequence is given by the recursive rule T1 is equal to minus 5, Tn plus 1 is equal to Tn plus 3 for n greater than or equal to 1. Find the first 5 terms of the sequence. Is 52 a term of this sequence? If so, which term is it? Page number 180. Question number 6. Let T1 be equal to 1, T2 is equal to 2, T3 is equal to 4 and Tn is equal to Tn minus 1 plus Tn minus 2 plus Tn minus 3 for n greater than or equal to 4. Find T4, T5, T6, T7 and T8. 8.4 Arithmetic Progressions. So far, we have learned that a sequence is an ordered list of numbers that may follow a particular rule. However, there may be sequences such as the sequence of prime numbers where there is no clear regularity in the rule. In this section, we explore a special kind of sequence called an arithmetic progression. Let us observe the growing pattern of squares given in figure 8.3. The first 4 stages of the pattern are given here. We have a figure here 8.3 which reflects figure 8.3 which exhibits growing pattern of squares. In stage 1, we have a red square. In stage 2, we have a red square in the center and 4 green squares at the corners of the red square. In stage 3, we have a square at the center and 4 green squares placed at the corners of the red square. In a similar way, 4 more squares are placed diagonally in this figure. In stage 4, repeating the previous pattern, we have 4 more green square diagonally placed along the diagonals with respect to the red square. If we count the number of tiny squares at each stage, we get sequence 1, 5, 9, 13. Think and reflect. Can you predict the number of squares in stage 5 and 6 of the sequence? In stage 10, 11 and 12. In stage 20. At any stage, we observe that at each stage 4 squares get added to the corners of the pattern in the earlier stage. The number of squares at successive stages can be written as 1, 1 plus 4, 1 plus 4 plus 4, 1 plus 4 plus 4 plus 4 and so on. Page number 181. This may be rewritten as 1, 1 plus 1 into 4, 1 plus 2 into 4, 1 plus 3 into 4 and so on. If we treat these expressions as the terms of a sequence, we get T1 is equal to 1, T2 is equal to 1 plus 1 into 4, T3 is equal to 1 plus 2 into 4, T4 is equal to 1 plus 3 into 4 and so on. We may therefore write the nth term as Tn is equal to 1 plus within brackets n minus 1 into 4, which simplifies to Tn is equal to 4n minus 3. The first 6 terms of the sequence representing the number of squares in figure 8.3 are 1, 5, 9, 13, 17, 21. We note that the difference between successive terms is the constant value 4. Such sequences in which the difference between consecutive terms is constant are known as arithmetic progressions. We will refer to them as APs. Think and reflect. Consider all the sequences we have discussed so far in this chapter. Which ones are arithmetic progressions and which ones are not? Can you justify your claim? Note that in the nth term, Tn is equal to 1 plus n minus 1 within brackets into 4 of the sequence given here. 1 is the first term of the sequence and 4 is the common difference. Similarly, the nth term of the sequence 1, 4, 7, 10 and so on is Tn is equal to 1 plus n minus 1 within brackets into 3, where 1 is the first term and 3 is the common difference. In the sequence 11, 7, 3, minus 1, minus 5 and so on, the numbers decrease by 4. This is also an arithmetic progression where the first term is 11 and the common difference is minus 4. In general, an arithmetic progression AP can be described as A plus D, A plus 2D, A plus 3D and so on, A plus n minus 1 within brackets into D, where A is the first term and D is the common difference. Thus, Tn is equal to A plus within brackets n minus, I repeat, Tn is equal to A plus within brackets n minus 1 into D is an expression for the nth term of any arithmetic progression for some fixed values of A and D. 8.4.1 Visualizing an AP. Let us return to the growing pattern of squares in figure 8.3 and prepare a table that exhibits the number of tiny squares at each stage. We have a tabular column here, first column reflecting about the stage number and the next one about the number of squares. For stage number 1, number of squares are 1. For stage number 2, number of squares are 5. For stage number 3, number of squares are 9. For stage number 4, number of squares are 13. For stage number 5, the number of squares are 17 and so on. For stage number n, the number of squares are 4n minus 3. Page number 182. Let us form a pair of numbers x, y. Using the information in the table given here, where x represents the stage number and y the corresponding number of squares. When we plot the ordered pairs emerging from the table, that is 1, 1, 2, 5, 3, 9, 4, 13, 5, 17, we observe that they lie on a straight line. This is given in the figure 8.4 here. Here we are given figure 8.4, which exhibits the growing pattern of squares represented by a linear pattern. On a graph sheet, we have x-axis and y-axis intersecting each other at origin O, and the points marked on x-axis are -2, 0, 2, 4, 6, 8 and 10. On y-axis, we have the points marked as 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. We also have points marked as 1.1, 2, 5. We have the points marked as 1, 1, 2, 5, 3, 9, 4, 13 and 5, 17. And we have a line joining these points represented here in the figure. Exercise: verify that The following sequences are arithmetic progressions and write their nth terms. What do you observe when you plot the ordered pairs emerging from them? First part 2, 5, 8, 11 and so on. Second part -5, -1, 3, 7 and so on. Exercise. Using the formula Tn is equal to A plus within brackets n minus 1 into D. Find the nth term of the following arithmetic progressions. First part 1 upon 2, 5 upon 2, 9 upon 2, 13 upon 2 and so on. Second part 1.5, 3.5, 5.5, 7.5 and so on. Note that Tn is equal to A plus within brackets n minus 1 into D is the explicit rule for finding the nth term of an AP. Page number 183. Can we also find the recursive rule? Yes, it is T1 is equal to A, Tn is equal to Tn minus 1 plus D for n greater than or equal to 2. Consider once again the AP 1, 5, 9, 13, 17 and so on. Since every term is 4 more than the previous term, another way of writing the sequence is T1 is equal to 1, Tn is equal to Tn minus 1 plus 4 for n greater than or equal to 2. Verify for yourself that this recursive rule leads to the terms of the sequence. Exercise. Find recursive rules for the APs in the previous exercises. Example 5. A person books a taxi to travel in the city. The taxi company charges a fixed booking fee of 200 rupees plus 40 rupees per kilometer travelled. Let us write the sequence representing the total fare after travelling 1 kilometer, 2 kilometer, 3 kilometer and so on. If the person travels 10 kilometers, what will be the total fare? Since the fixed amount is 200 rupees, after 1 kilometer the fare will be 200 rupees plus 40 rupees, that is equal to 240 rupees. After 2 kilometers it will be 200 rupees plus 80 rupees, that is equal to 280 rupees. And after 3 kilometers it will be 200 rupees plus 120 rupees, that is equal to 320 rupees. The sequence 240, 280, 320 and so on is an AP with first term 240 and common difference 40. The nth term of the sequence is 240 plus within brackets n minus 1 into 40, that is equal to 240 plus 40n minus 40, that is equal to 200 plus 40n, where n represents the distance travelled in kilometers. 8.5. Sum of the first n natural numbers. In this section, we derive a simple yet important rule for the sum of the first n natural numbers. To begin with, can you find the sum of the first 10 natural numbers without actually adding all of them? Let us try a unique approach. Let S denote the sum of the first 10 natural numbers. Thus, S is equal to 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. We can also write it as S is equal to 10 plus 9 plus 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1. If we place these two equations one below the other, we notice something interesting. S is equal to 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10, and S is equal to 10 plus 9 plus 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1. each pair of corresponding numbers 1 plus 10, 2 plus 9, 3 plus 8 and so on, 10 plus 1 in the two equations add up to 11. Adding the two equations for s, we get 2s is equal to 11 plus 11 plus 11 plus so on plus 11. That is 11 added 10 times. This leads to 2s is equal to 110 or s is equal to 55. The sum of the first 10 natural numbers is indeed 55. Page number 184. Think and reflect. Can the same approach be used to find the sum of 1 plus 2 plus 3 plus so on plus 100? This method of writing the sum from 1 to any number, reversing the sum and then adding the two expressions can be used to arrive at the formula for the sum of first n natural numbers for any value of n. Let s be equal to 1 plus 2 plus so on plus n. Then s is equal to n plus n minus 1 within brackets plus so on plus 1. So 2s is equal to n multiplied by n plus 1 within brackets. We conclude s is equal to n multiplied by n plus 1 within brackets upon 2. We can also think of this argument pictorially. The diagram in figure 8.5 represents the method to find the sum 1 plus 2 plus 3 plus 4 plus 5 plus 6. Note that the figure comprises two sets of circles that represent the sum 1 plus 2 plus 3 plus 4 plus 5 plus 6 above and below of the jigsaw partition. The total number of circles forms a 7 by 6 rectangular array. In figure 8.5, we can find that the circles have been represented in two colors, red and green. These circles represent 2 multiplied by within brackets 1 plus 2 plus 3 plus 4 plus 5 plus 6, that is equal to 7 into 6. We have 7 rows and 6 columns. Thus, figure 8.5 represents the fact 2 multiplied by within brackets 1 plus 2 plus 3 plus 4 plus 5 plus 6 is equal to 7 into 6. This can similarly be extended to find the sum 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10, namely 2 multiplied by within brackets 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10, that is equal to 10 into 11. In general, 2 multiplied by within brackets 1 plus 2 plus 3 plus 4 plus so on plus n is equal to n into within brackets n plus 1. Therefore, 1 plus 2 plus 3 plus 4 plus so on n is equal to n into n plus 1 upon 2. If we use the notation Sn to represent the sum of the first n natural numbers, then Sn is equal to n multiplied by n plus 1 upon 2. Page number 185. The first known written mention of this result can be found in Aryabhatta's Aryabhatiya, chapter 2, verse 19. The verse provides two ways to calculate the sum, with the second part describing that the sum can be calculated by taking the sum of the first and last terms divided by 2 within brackets the average and multiplied by the number of terms. Think and reflect. Can you use this formula to find S20, S50 or S1000? Also, This formula can be used to find the sum of consecutive numbers such as 25 plus 26 plus 27 plus so on plus 58. Note that 25 plus 26 plus 27 plus so on plus 58 is equal to within brackets 1 plus 2 plus 3 plus so on plus 58 minus within brackets 1 plus 2 plus 3 plus so on plus 24. That is equal to S58 minus S24. That is equal to 58 into 59 upon 2 minus 24 into 25 upon 2. That is equal to 29 into 59 minus 12 into 25. That is equal to 1711 minus 300. That is equal to 1411. Think and reflect. Let us revisit the sequence Tn of triangular numbers 1, 3, 6, 10, 15 as given in figure 8.1. Note that the nth term of the sequence is the sum of the first n natural numbers. Thus, Tn is equal to n into n plus 1 upon 2. Can you use this to find the 10th, 17th and 80th triangular numbers? Exercise set 8.2. Question number 1. Find the 10th and 26th terms of the AP 3, 8, 13, 18 and so on. Question number 2. Which term of the AP 21, 18, 15 and so on is minus 81? Also, is 0 a term of this AP? Give reasons for your answer. Question number 3. Find the nth term of the AP 11, 8, 5, 2 and so on. Write the recursive rule for this AP. Question number 4. An AP consists of 50 terms in which the third term is 12 and the last term is 106. Find the 29th term. Hint provided is, if A is the first term and D is the common difference, then we arrive at the equations A plus 2D is equal to 12 and A plus 49D is equal to 106. Solve this pair of linear equations for A and D. Page number 186. Question number 5. How many two-digit numbers are divisible by 3? What is the sum of all these two-digit numbers? Question number 6. Harish started work at an annual salary of 5 lakh rupees and received an increment of 20,000 rupees each year. After how many years did his salary income reach 7 lakh rupees? Question number 7. A child arranges marbles in rows so that the first row has 1 marble, the second has 2 marbles, the third has 3 and so on up to 25 rows. How many marbles does the child use in all? 8.6. Geometric progressions. In this section, we explore yet another special kind of sequence called a geometric progression within brackets GP. Consider the growing pattern of squares as represented in figure 8.6. The first 4 stages of the pattern are exhibited here. In stage 1, we have 3 squares. In stage 2, we have 6 squares. With 3 arranged in a row, the 3 squares have been arranged in another row. In stage 3, we have 3 squares arranged in 4 rows. In stage 4, we have 8 rows arranged in 3 columns. In figure 8.6, here the growing pattern of squares has been exhibited. If we count the total number of green squares in the 4 stages of the pattern, we get the sequence 3, 6, 12, 24. Think and reflect. Can you predict the number of squares in stage 5 and 6 of the pattern? In stages 10, 11 and 12? In stage 20? At any stage? How is this different from the growing pattern in figure 8.3? We observe that at each stage, the number of green squares is doubled or is twice the number of squares in the previous stage. The number of squares at successive stages is 3, 3 plus 3 is equal to 6, 6 plus 6 is equal to 12, 12 plus 12 is equal to 24, and so on. These may be rewritten as 3, 3 into 2, 3 into 4, 3 into 8, or as 3, 3 into 2, 3 into 2 square, 3 into 2 cube, and so on. Page number 187. If we treat these expressions as the terms of a sequence, we get T1 is equal to 3, T2 is equal to 3 into 2, T3 is equal to 3 into 2 square, T4 is equal to 3 into 2 cube, and so on. We can write the nth term as Tn is equal to 3 into 2 to the power n minus 1. As a recursive formula, we can write T1 is equal to 3 and Tn is equal to 2 into Tn minus 1 for n greater than or equal to 2. The first 6 terms of the sequence are 3, 6, 12, 24, 48, 96. Each term of the sequence is obtained by multiplying the previous term by 2. This constant multiplier is also known as the common ratio of the sequence. We observe that the ratios of consecutive pairs of terms are all the same. 6 upon 3 is equal to 12 upon 6, that is equal to 24 upon 12, that is equal to 48 upon 24, that is equal to 96 upon 48, that is equal to 2. Such a sequence with a common ratio is known as a geometric progression or GP. In general, a GP may be described in the form of a sequence as A, AR, AR square, AR cube, and so on, AR raised to n minus 1, where A is the first term, R is the common ratio, and Tn is equal to AR to the power n minus 1 is the nth term. Example 6 is 1, 2, 4, 8, 16 and so on a geometric progression? If so, what is the common ratio? Example 7 is 1, 3, 9, 27, 81 and so on a geometric progression? If so, what is the common ratio? Example 8 is 1, minus 1, 1, minus 1, 1 and so on a geometric progression? If so, what is the common ratio? Example 9. Check whether the sequence 5, 15 upon 4, 45 upon 16, 135 upon 64 and so on is a geometric progression and find its nth term. In the given sequence, T1 is equal to 5, T2 is equal to 15 upon 4, T3 is equal to 45 upon 16, T4 is equal to 135 upon 64. Let us evaluate the ratios of consecutive pairs of terms. T2 upon T1 is equal to 15 upon 4 divided by 5, that is equal to 15 upon 4 into 1 upon 5 is equal to 3 upon 4. T3 upon T2 is equal to 45 upon 16 divided by 15 upon 4, that is equal to 45 upon 16 into 4 upon 15 is equal to 3 upon 4. T4 upon T3 is equal to 135 upon 64 divided by 45 by 16 is equal to 135 upon 64 into 16 upon 45 is equal to 3 upon 4. The ratio of consecutive pairs of terms is a constant 3 upon 4. Hence, the given sequence is a GP with A is equal to 5 and R is equal to 3 upon 4. The nth term is equal to A into R to the power n minus 1, that is equal to 5 into 3 upon 4 whole raised to n minus 1. Substitute n is equal to 1, 2, 3 and so on in this expression to check if you get the terms of the given sequence. Page number 188. Exercise. Check whether the following sequence are geometric progressions and find their nth terms. First part 2, 10, 50, 250 and so on. Second part 4, 8 upon 3, 16 upon 9, 32 upon 27 and so on. Third part 3, minus 3 upon 2, 3 upon 4, minus 3 upon 8 and so on. Exercise. Can you find a recursive rule for the formula Tn is equal to T into 10 to the power n minus 1 that generates the geometric progression 3, 30, 300, 3000 and so on. 8.6.1 Fun with fractals. Recall from grade 8. Another interesting pattern as exhibited in figure 8.7. Stage 0 represents a piece of paper cut in the shape of an equilateral triangle. Let us join the midpoints of the three sides of the triangle leading to four smaller equilateral triangles. Now remove the central triangle. You will get the figure in stage 1 with a triangular hole in the center. Repeat the process on all three black triangles in stage 1. This will lead to the figure in stage 2. In a similar manner, we arrive at stage 3 from stage 2. The process can be continued forever. This fascinating pattern is known as Sierpinski triangle. This is actually a fractal. We will learn more about fractals in a later grade. In figure 8.7, we have the different stages of the fractals represented by Sierpinski triangle. In stage 0, the whole triangle is black. In stage 1, we have a triangle at the center as white and three black triangles on the sides of the triangle. And in stage 2, we have a bigger triangle at the center and the same pattern on the three sides of the triangle. And in stage 3, again this pattern repeats and we have a middle triangle and three smaller triangles and the same pattern with three more tiny triangles in each part of the triangle. Vaclav Sierpinski 1882 to 1969 was a Polish mathematician known for his numerous contributions to mathematics, including the Sierpinski gasket, one of the earliest and most famous examples of a fractal. Page number 189. Think and reflect. Observe the Sierpinski triangle and try to answer the following questions. A. How many black triangles are there in stage 0 to stage 3 of figure 8.7? B. Can you predict the number of black triangles at stage 4 and 5? C. Can you find a rule for the number of black triangles at the nth stage? D. Suppose the area of the triangle, that is the black region in stage 0, is 1 square unit. What is the area of the black region in stages 1, 2 and 3? What will be the area of the black region in stages 4 and 5? Find a rule for the area of the black region at the nth stage. What happens to this area as n, the number of stages goes on increasing? We observe that the number of black triangles is 1, 3, 9 and 27 in stages 0, 1, 2 and 3 respectively. In fact, in every stage, each black triangle is replaced with 3 smaller triangles at the next stage. Thus, the number of black triangles at every stage is 3 times the number at the previous stage. At stages 4 and 5, the number of black triangles will be 81 and 243. Note that the sequence 1, 3, 9, 27, 81, 243 and so on is a GP, since every successive term of the sequence can be obtained by multiplying the previous term by 3. Also, all the terms of the sequence are powers of 3. 1 is equal to 3 to the power 0, 3 is equal to 3 to the power 1, 9 is equal to 3 to the power 2 and so on. Continuing in this manner, we observe that the exponent of 3 matches the stage number as given in table 1. Thus, the number of black triangles at the nth stage of the Sierpinski triangle is given by 3 to the power n. The number of black triangles increases very quickly as the stage numbers increase. Can you explain why? What about the area of the black region? In stage 1, the equilateral triangle at stage 0 is divided into 4 equal parts and the central part is removed. This means that if the black region at stage 0 is 1 square unit, then the black region at stage 1 is 3/4 square units. This process is repeated on stage 1 to arrive at stage 2. Hence, the black region at stage 2 will be 3/4 of the black region of stage 1, which is equal to 3/4 into 3/4, that is equal to 3/4 whole square. Can you explain why the area of the black region at stage n will be 3/4 whole raised to n? The area of the black region at each stage also leads to a geometric progression where every successive term of the sequence is obtained by multiplying the previous term by 3/4. Page number 190. Thus, the number of black triangles increases rapidly. The total area of the triangle decreases. We have a tabular column here which exhibits the stage, number of black triangles Tn and shaded area Sn. So for stage 0, we have number of black triangles to be 1, that is equal to 3 to the power 0, and shaded area Sn is equal to 1. For stage 1, number of black triangles Tn is equal to 3 is equal to 3 to the power 1 and shaded area Sn is equal to 3/4. For stage 2, the number of black triangles is 9, that is equal to 3 square, and the shaded area Sn is equal to 3/4 whole square. For stage 3, the number of black triangles is 27, that is equal to 3 cube, and the shaded area Sn is equal to 3/4 whole cube. For stage 4, the number of black triangles is 81, that is equal to 3 to the power 4, and the shaded area Sn is equal to 3/4 whole raised to 4. For stage 5, the number of black triangles is 243, that is equal to 3 to the power 5, and the shaded area Sn is equal to 3/4 whole raised to 5, and so on. And the last stage n, the number of black triangles Tn will be equal to 3 to the power n, and the shaded area Sn will be equal to 3 upon 4 whole raised to n. The explicit formula for the number of black triangles and the area of the black region at any stage is given by Tn is equal to 3 to the power n and Sn is equal to 3 upon 4 whole raised to n. Respectively, the recursive rules for the same are T1 is equal to 1, Tn is equal to 3 into Tn minus 1 for n greater than or equal to 2, and S1 is equal to 1, Sn is equal to 3 upon 4 into Sn minus 1 for n greater than or equal to 2. Fractals are shapes or patterns that repeat themselves at different scales. This means that if you zoom in on a small part of a fractal, it looks similar to the whole. Fractals are found throughout nature, like in the branching of trees, in vegetables such as cauliflower or broccoli, in the shape of snowflakes, or in the patterns of coastlines. They can be created using simple rules, but can form very complex and beautiful designs. Fractals help us understand patterns in nature and also lead us to important concepts in mathematics. Here in figure 8.8, we have pictures of cauliflower and coastline and also some patterns of fractals given here of snowflakes. 8.6.2 Visualizing a GP. Let us revisit the growing pattern of squares in figure 8.6 and prepare a table that exhibits the number of green squares at each stage. Page number 191. We have a tabular column here which exhibits the stage number and number of squares. For stage number 1, the number of squares is 3. For stage number 2, the number of squares is 6. For stage number 3, the number of squares is 12. For stage number 4, the number of squares is 24. And for stage number 5, the number of squares is 48. And so on. For stage number n, the number of squares is 3 into 2 to the power n minus 1. Let us consider the pairs of numbers xy, where x represents the stage number and y the corresponding number of squares. When we plot the ordered pairs emerging from the given table, that is 1, 3, 2, 6, 3, 12, 4, 24, 5, 48, we observe that they do not lie on a straight line. This is given in figure 8.9. Similarly, when we plot the pairs of numbers x, y, where x represents stage number and y the number of black triangles in the Sierpinski triangle, we get the graph in figure 8.10a. Figure 8.10b exhibits the graph where stage numbers are represented on the x-axis and the area of the black region of the stages on the y-axis. The graphs tell us that as the stage numbers increase, the number of shaded triangles increases very quickly, whereas the area of the black region diminishes, getting closer and closer to 0. Here in figure 8.9, we have points emerging from a GP do not lie on a straight line. We have a graph here. On x-axis, we have points marked as 0, 1, 2, 3, 4, 5. On y-axis, the numbers marked are 0, 5, 10, 15, 20, 25, 30, 35, 45, 50. We also have points marked as 1, 3, 2, 6, 3, 12, 4, 24, 5, 48. These points have been joined and they represent a curve. Page number 192. In figure 8.10a, we have points emerging from a point arising out of the stages of the Sierpinski triangle. We have two graphs here, graph A and graph B. In graph A, we have x-axis with points -2, 0, 1, 2, 3, 4, and on y-axis we have points 0, 10, 20, 30, 40, 50, 60, 70 and 80. We also have points marked on this graph as 01, 13, 29, 327, 481, and these points when joined are forming a curve. In figure 8.10b, we again have a graphical representation. On x-axis, the numbers marked are 0, 1, 2, 3, 4, 5, and on y-axis, we have the numbers marked as 0, 0.2, 0.4, 0.6, 0.8, 1, 2, 1, 1.2. We also have points marked as 0, 1, 1, 0.75, 2, 0.56, 3, 0.42, 4, 0.32. These points when joined form a curve. Here is another example in which a GP arises. Example 10. A ball is dropped from a height of 24 feet above the ground. Each time, the ball bounces up to 3/4 of its previous height. Part A. Can you write the sequence of numbers obtained from the heights attained by the ball in 5 successive bounces? Part B. How many bounces are required for the ball to remain below a height of 1/6 of the original height from which it was dropped? The sequence of maximum heights attained by the ball after each bounce is: first bounce 24 into 0.75, that is equal to 18 feet. Second bounce 18 into 0.75 is equal to 13.5 feet. Third bounce 13.5 into 0.75 is equal to 10.125 feet. Fourth bounce 10.125 into 0.75 is equal to 7.59375 feet. Fifth bounce 7.59675 into 0.75 is equal to 5.695 feet. Sixth bounce 5.695 into 0.75 is equal to 4.27125 feet. Seventh bounce 4.27125 into 0.75 is equal to 3.2034375 feet. Page number 193. Here we have figure 8.11 where we can find a graphical representation. On the x-axis, we have the numbers marked as 0, 1, 2, 3, 4, 5, 6, 7 on x-axis, and 5, 10, 15, 20, 25 on y-axis. The y-axis represents the height in feet and x-axis represents the number of bounces. For 0, we have 24.00 feet. For 1, we have 18.00 feet. For 2, 13.50 feet. For 3, 10.12 feet. For 4, 7.9 feet. For 5, 5.70 feet. For 6, 4.27 feet. For 7, 3.20 feet. The sequence of the height forms a GP with A is equal to 18 and R is equal to 0.75. or 3 upon 4, that is 18, 13.5, 10.125, 7.594, 5.695, 4.27125, 3.2034375, and so on. We observe that after the 7th bounce, the ball remains below 1/6 of the height at which it started. Exercise set 8.3. Question number 1. Find the 12th term of a GP with common ratio 2 whose 8th term is 192. Question number 2. Find the 10th and nth terms of the GP 5, 25, 125, and so on. Question number 3. A sequence is given by the recursive rule T1 is equal to 2, Tn plus 1 is equal to 3 into Tn minus 2 for n greater than or equal to 1. Which term of the sequence is 730? Question number 4. Which term of the GP 2, 6, 18, and so on is 4374? Write the explicit formula as well as the recursive formula for the nth term. Question number 5. A ball is dropped from a height of 80 meters. After hitting the ground, it bounces back to 60% of the height from which it fell. It continues bouncing in this way, each time rising to 60% of the previous height. First part. What height does the ball reach after the 5th bounce? Second part. What is the total vertical distance the ball has travelled by the time it hits the ground from the 6th time? Second part, I repeat, what is the total vertical distance the ball has travelled by the time it hits the ground for the 6th time? Page number 194. Question number 6. Which term of the sequence 2, 2 square root 2, 4, and so on is 128? Question number 7. Figure 8.12 exhibits stages 0 to 3 of the Sierpinski square carpet. Stage 0 of this fractal is a square sheet of paper. To construct stage 1, each side of the square is trisected and the points of trisection of opposite sides are joined to obtain 9 smaller squares. The center square is then removed and the 8 smaller squares are retained, leaving a square hole in the center. The same process is repeated on the 8 smaller shaded squares to obtain stage 2 and so on. The stages have been represented in figure 8.12 here. Stages 0, 1, 2 and 3 of the Sierpinski square carpet have been exhibited at various stages here. Stage 0, stage 1, stage 2 and stage 3 as described above. Look at figure 8.12 and try to answer the following questions. Part 1. How many red squares are there in stages 0 to 3? Second part. Can you predict the number of red squares in stages 4 and 5? Third part. Can you find a rule for the number of red squares at the nth stage? Write the explicit formula as well as the recursive formula for the number of red squares at any stage. Fourth part. Suppose the area of the square in stage 0 is 1 square unit. What is the area of the red region in stages 1, 2 and 3? What will be the area of the red region in stages 4 and 5? Find the explicit as well as the recursive formula for the area of the red region at the nth stage. What happens to this area as n, the number of stages goes on increasing? End of chapter exercises. Question number 1. Find the 31st term of an AP whose 11th term is 38 and 16th term is 73. Question number 2. Determine the AP whose third term is 16 and whose 7th term exceeds the 5th term by 12. Page number 195. Question number 3. How many 3-digit numbers are divisible by 7? The hint provided is all 3-digit numbers divisible by 7 form an AP. Find the smallest and largest such 3-digit numbers. Question number 4. How many multiples of 4 lie between 10 and 250? Hint provided is all multiples of 4 form an AP. Find the smallest and largest multiples of 4 between 10 and 250. Question number 5. Find a GP for which the sum of the first two terms is -4 and the fifth term is 4 times the third term. Question number 6. Find all possible ways of expressing 100 as the sum of consecutive natural numbers. Question number 7. The number of bacteria in a certain culture doubles every hour. If there were 30 bacteria present in the culture originally, how many bacteria will be present at the end of the second hour, fourth hour and nth hour? Question number 8. The sum of the fourth and eighth terms of an AP is 24 and the sum of the sixth and 10th terms is 44. Find the first 3 terms of the AP. Question number 9. Find the smallest value of n such that the sum of the first n natural numbers is greater than 1000. Question number 10. Which term of the GP 2, 8, 32 and so on is 1,31,072? Write the explicit formula as well as the recursive formula for the nth term. Question number 11. The sum of the first 3 terms of a GP is 13 upon 12 and their product is -1. Find the common ratio and the terms. Question number 12. If the 4th, 10th and 16th terms of a GP are X, Y and Z respectively, prove that X, Y, Z are in GP. Question number 13. The sum of the first 3 terms of a geometric progression is 26 and the sum of their squares is 364. Find the terms of the GP. Question number 14. Suppose P1 is equal to 1, P2 is equal to 2 and for n greater than 2, Pn is equal to P1 plus P2 plus so on plus Pn minus 1 plus 1. Find the values of P1, P2 and so on P8. Can you find a simpler recursive formula for Pn? Can you give an explicit formula? Question number 15. Suppose W1 is equal to 1, W2 is equal to 2 and for n greater than 2, Wn is equal to W1 plus W2 plus so on plus Wn minus 2 plus 2. Find the values of W1, W2 and so on W8. Do you recognize this sequence? Page number 196. Chapter Summary. First point. A sequence is an ordered list of numbers. Each number in the list is called a term. Second point. A general formula or rule for a sequence is a rule that can be used to generate each term. An explicit formula is a rule that uses the term's position number n to calculate the term's value. Third point, A recursive formula is a rule that gives the value of a given term using the values of previous terms. Fourth point, the triangular number of sequence is given by 1, 3, 6, 10, 15 and so on. Each term is the sum of the natural numbers up to the position of that term. The nth term is given by Tn is equal to n into n plus 1 upon 2, which is also the formula for the sum of the first n natural numbers. Fifth point, an arithmetic progression AP is a list of numbers in which each term after the first term is obtained by adding a fixed number d to the previous term. The fixed number d is called the common difference. Sixth point, the nth term of an AP is given by Tn is equal to a plus n minus 1 within brackets into d, where a is the first term and d is the common difference. The general form of an AP is a plus d, a plus 2d, a plus 3d and so on. A plus within brackets n minus 1 into d. Seventh point, a geometric progression GP is a list of numbers in which each term after the first term is obtained by multiplying the previous term by a fixed number. This constant factor r is called the common ratio. Eighth point, the nth term of a GP is given by Tn is equal to a r to the power n minus 1, where a is the first term and r is the common ratio. The general form of a GP is a, ar square, ar cube and so on, ar raised to n minus 1. Ninth point, many attributes of fractals such as the Sierpinski triangle and the Sierpinski square carpet leads to geometric progressions. Chapter 8 ends here.
Ganit Manjari, Part 1. You were just listening to this audiobook, Textbook of Mathematics for Grade 9. Narration, Swarnlata Sharma. Sound recordist, Prasoon Kumar. Assistance in production, Kusumlata. Directed and produced by Vimlesh Chaudhary. This audiobook is brought to you by CIET NCERT, New Delhi, India.